All right, let's get going. Welcome, everyone. I'm sure that, again, people are going to show up once we start the talk. Welcome back to another segment of the BEG seminar series. Today we have back, actually, Xinming Wu back to giving a talk. Xinming received a PhD in geophysics from Colorado School of Mines, where he was a member of the Center for Wave Phenomena. And as some of you remember, he was a postdoc here at the Bureau between 2016 and 2019. He's currently a professor of geophysics at the University of Science and Technology in China, where he founded the Computational Interpretation Group, mainly focusing on computational methods for processing and interpreting geoscience data. He received several awards from SCG, including the Kircher Award in 2020, also honorary SCG honorary lecturer in 2020, and some best paper awards from geophysics and SCG annual convention. He actively contributes to a geophysical community as an SCG council member and as an associate editor for the journal Geophysics, Computers and Geosciences. And some of you remember when Xinming was here, that when we were getting the BEG monthly peer-reviewed publication updates, every other paper was a Wu et al. Paper, so he's a very productive author. So welcome back, Xinming, and looking forward to your talk. And today he will be giving us a talk on leveraging pre-trained foundational methods for geophysical applications. Xinming, take it away.
Okay, thanks, Andres, for the introduction. And good morning, everyone. And thank you very much for attending my presentation. And today I would like to share some of our latest work on adapting pre-trained foundation models for geophysical applications. And as Andrews just mentioned, that I was also a previous member at BEG from 2016 to 2019. And where I worked as a postdoc with Dr. Sergey Fomor. So you can see here, this is me in this picture. And there I actually had very broad and successful collaborations with the many smart researchers there at BEG. And I enjoyed very much the 3 years of my research and my life with my family at Austin. So today I'm so happy that I have this opportunity to present at the BEG seminar again. And I would like to especially thank Dr. Xuesong Ding for the invitation, and thanks Jennifer and other staff for organizing the seminar. And back to the presentation, and today I would like to focus on two topics. So the first one is about adapting pre-trained foundation models for geophysical applications. And the second one is actually about how to build geophysical dataset, because the dataset, I think, is the most important for developing AI applications in geophysics. So first, let's talk about the foundation model adaptation for geophysical applications. And we all know that in recent years, the rise of foundation models in natural language, image, and video processing has sparked a new revolution in artificial intelligence. And these foundation models are large parameter models pre-trained on massive datasets by self-supervised or semi-supervised learning, and they can be fine-tuned or prompted to perform various downstream tasks. And recently, the emerged large parameter models like ChatGPT-4, the DALL-E 2, and the segment anything model demonstrate powerful feature extraction capability and superior generalization abilities in different tasks. And developing these foundation models is now actually the central to AI research across various fields. But in geophysics, unfortunately, we not yet has a good foundation model in geophysics. So therefore, in this presentation, we'll explore the feasibility of directly adapting the pre-trained foundation models from other fields to the geophysics. And considering that geophysical data can essentially be viewed as time series signals or high dimension matrices or tensors. which are actually similar to speech, images, and videos. So therefore, we think that the ability of the pre-trained models to extract general features from time series or high-dimensional images should be also applied to extract critical features from geophysical data. So we believe that by designing appropriate adaptation modules and fine-tune strategies, these foundation models should be able to transfer to tasks in geophysics. So first, let's discuss the adaptation of the Meta's visual foundation model, computer vision foundation model called DALV2 for geophysical data analysis. And here we present our entire adaptation process. And we start by constructing some small geophysical data sets for different tasks. Here in the whole workflow, we use the pre-trained foundation model DALV2 for the and we use it as the data encoder to extract features from input data, and then we implement some fine-tuning techniques combined with various types of decoders to adapt the DALV2 the encoder's powerful feature extraction capability to specific geophysical downstream tasks like the fishes classification, geobody segmentation, and some like denoisy tasks. So before delving into the technical details of DALV2 adaptation, let's briefly understand what is DALV2. And DALV2 is basically the architecture of this model is a vision transformer, and it is pre-trained using contrastive learning, and its training data is critical, and it consists of 1.2 billion images sourced from various data sets and the internet, which is further cleaned down to only 142 million augmented and curated data sets for the pre-training. And this data curation and augmentation is actually very important, as discussed in the paper. But we actually in geophysics we do not have this kind of carefully curated data sets for training. So this is one reason why it is really hard to develop a geophysical foundation model. So the table below actually includes some ablation experiments which show that the model pre-trained on the curated dataset is actually significantly perform better than across very different tasks compared to the model pre-trained on the uncurated data. So here we want to see that the data before the curation is actually the dataset is larger than the one after curation, but the model trained on the curated data with a smaller size of data samples actually performs better than the one trained on the original data set, which has more samples. So this experiments show that the data curation is very important for the training. And the DALV2 actually comes in 4 different versions with the parameters counts ranging from 20 million to 1.1 billion. And compared to other convection foundation models, as shown in this table, DALV2 demonstrates more powerful performance on many test datasets compared to some other models. So this is one reason why we want to choose DALV2 as an example for the adaptation. And to understand why DALV2 excels in tasks such as image segmentation and classification, and the original paper actually analyzed the ability to encode key features of natural images, as shown in this slide. And this analysis is done through some like principal component analysis, that's like PCE feature extracted by DLV2, illustrating how it represents the original image in the feature space or in the encoding space. So these images are the input, and these are the features extracted by the DLV2, the encoder. And in these examples, we can see that each target and its background are accurately and completely represented by the in the space domain, in the latent space domain, by the encoder. And the very interestingly, different parts of the targets, as for example, as shown in this in this image, the bird's head, the body, and the wings are actually clearly separated. And this demonstrates that the elevator's ability to understand and represent the key image features. And this is very important for various image-related tasks like segmentation and classification. Right? And if we can represent the image in the space, in the features space domain, like this one shown here, we believe that the network will be able to perform very well for these image related tasks. And given the DLV2's strong performance in understanding and representing the natural image features, so the question is that, can it also effectively handle the geophysical data? And to answer this question, we actually did some tests. So by directly input the geophysical data like seismic images, the depth images, and the lunar images into the pre-trained DLV2, and then we do the same analysis in the feature space to do the PCE, apply the PCE analysis to the feature space of the DLV2, and show only the three most dominant components in RGB colors, as shown in this color in this vertical colors. And you can see that. So we found that although that it has some ability, it generally has some ability to understand and represent the key geophysical features. But we can see that the performance is not as good as with in the natural images shown previously in this net, right? So therefore if we look carefully, some key targets and their backgrounds in geophysical data are also less detailed and complete in the feature space. So therefore, if we directly using DLV2 to extract geophysical features for the downstream tasks, and the performance might be limited, right? So therefore, to better adapt the DLV2 to geophysical data, we fine-tune it using some small geophysical data sets. And here we show the effect of this adaptation on this geophysical data. And you can see that after the fine-tuning, the key targets and their backgrounds are now much more accurate and more completely represented by the adapted DLV2. And also we can observe much richer details in these features extracted by the adapted DLV2 model. So if we do some further downstream tasks based on these features after the fine-tuning, then we can expect good performance, right? And now let's introduce of the entire adaptation and fine-tuning processing for DLV2. And first, we collected and constructed some small geophysical labeled datasets for different tasks, including some open source datasets related to seismic fishes classification and the soil body segmentation, and also some datasets for fall detection, which these are manually labeled by ourselves, and some lunar crater detection, and also the depth earthquake event detection. And if we look at this, the table of this data sets, we can see that the number of the training samples for each task is relatively small, ranging from only 100 samples to 3,000 samples. And we tested whether effective fine-tuning of the pre-trained model can be achieved by using such a small size of training samples. And also for comparison, we used the traditional UNet and the derivative combined with various decoders, including the simplest MLP and the more complex PUP, MLA, and the DPT decoders for the comparison. And the PUP and the MLA are effective in segmentation tasks. And these are the decoders that we used to collect to the encode of the derivative. And with the PUP being a progressive upsampling decoder, which is similar to the decoder of the UNet. And the MLA uses multiple score feature fusion from different encoder layers. And the DBT is another common decoder that used for the fine-tuning, which is more suitable for dense prediction tasks, similar to UNet as well, which added skip collections for detailed feature attention. And the fine-tuning strategy is important due to the significant differences between the geophysical data features and the derivatives pre-training datasets, which are only natural images, right? So here for the fine-tuning strategy, we use LoRa, which is the most common fine-tuning strategy used to adapt the foundation models. And this in this strategy, it decomposes a weight. So W0 is the original weight matrix, which is huge for the original foundation model. So and we decompose the weight changes of the pre-trained model into two low rank matrices B and A. And the parameters of these two matrices will be much smaller than the original the matrix of W0. So and therefore we can the fine tuning will be very efficient and can avoid overfitting during the fine tuning, because in the fine tuning we use only some small size of training samples. So it's if we have too many weights for the fine tuning parameters for the fine tuning, then it will be easily get overfitting. But because the rank of these two matrices are very small, so the weights with the parameters in these two matrices actually are very like a few. So here we show some fine-tuning results of derivative on different geophysical dataset tasks. So for the first task, it's a seismic features classification. And here we can see that we use derivative collected to different types of decoders, including some simple linear and also PUP, DPT, and MLP decoders, as I just introduced in the previous slides. And we compare these results with the UNet. This UNet is fully trained by using the datasets which is the thing which is also used for the fine tuning of these foundation models. And we can see that the foundation model, the derivative after the fine tuning by using the same dataset actually performs better than the UNet for this seismic features segmentation task. And we also observe that if we look at these curves, we can observe that the UNet's performance drops quickly. This blue curve drops very quickly for the sections that are far from the training samples. But the fine-tuned derivative remains more stable and indicating its stronger generalization abilities. And for the other task is about the south body segmentation. And we can also see that the derivative combined with some decoders fine-tuned by using the scintillator set, it performs pretty well and better than the one achieved by the UNet. Let's move to another application, which are the lunar curated detection, which is also slightly more we can also observe that the foundation model has some advantage than the UNet for the segmentation. And here for the fault detection, we focus on the deeper faults, which are actually very difficult to detect or segmentation previously by using some deep learning like UNet or Delavit or deep lab networks, because this fault has a very large scale. It needs a very large receptive field to be able to detect these large scale faults. But we can see that the foundation model after the fine tuning is able to detect most of these large scale faults much better than the one by the UNet. And again, for the earthquake detection from the depth arrays, we can also observe some similar results. So this is the example that we successfully adapting DLV2 for geophysical data analysis or interpretation. And here we want to introduce another work which is also similar to the previous one. We are adapting another foundation model called segment anything model with some promptable with some human prompts for the interactive geophysical interpretation, seismic interpretation. So here we introduce a prompt engine to achieve some expert interactions, and further, which actually helpful to enhance the model's generalization and the performance. And we build this in this work. We are trying to build a universal model which is capable of interpreting like segment all kinds of geobodies in seismic data by integrating proper encoders with different types of constraints. So here we basically want to build one model for all geobodies. So previously, in the deep learning methods, we will, for each type of geobodies, we need to train a separate deep learning model for each type of geobodies, right? But here we want to see if we can train one model which is capable to interpret all kinds of different geobodies. And here in this model, we allow different types of prompts to get the interpretation. And these prompts include some points, box, and some like well-lock mask. So these three different types of prompts can be combined together. They can be mixed. And so you can, of course, you can use only one prompt as the constraints as the guidance for the interpretation. You can also use multiple type of these prompts for the constraints. So here is the network, the architecture, network architecture that we used for the fine tuning or adapting this model for with the prompt encoder. So as shown here in this block, this is the pre-trained encoder with the pre-trained parameters we used from a pre-trained vision foundation model, like DLV2 or like segment anything. And here we use this pre-trained model as encoder to extract features from the input geophysical data or seismic image. And of course, we need to adapt this encoder, this foundation model, by using some neural layers. And also, we design another proper encoder, which allow us to input some human interactions like points, box, and the well-lock mask. And also, we need to design a mask decoder, which is actually fully updated, fully trained during the adaptation. So during the fine tuning, this part and this part, the neural layers, the prop encoder, and the mask decoder are fully trained, and the encoder is with large pre-trained parameters is actually frozen during the adaptation. It's not updated during the training. And to train this model to be able to interpret all kinds of geobodies, we prepared a mixed training data sets with different types of geobodies like karsts, salt bodies, channel bodies, and sediment layers. So these data sets are not separated. We combine these data sets together to form a mixed data set and use this mixed data set to train to fine tune this framework to so that this model is able to interpret any types of geobodies. And now let me show you some results. And we can see that before and after the fine tuning, this model is after the fine tuning, this model works much better than before fine tuning to detect this geobody, these geological layers. And here we want to visually interpret how the prop impacts the model for the feature extraction. And here on the left show an example with which is a 2D seismic image, and the red area, the red color indicate the target layer that we want to segment from this input seismic image. And here we add firstly we add one point to indicate this is the target layer that we want to interpret. And you can see that the network, the decoder, this is the feature map that we extracted from the decoder. And it shows that the features near this target layer is highlighted by the red color, which shows with the relatively high probability. But this area is larger than the target area. For example, above this target area, we can still see these relatively high features, high probability features. But then if we add a box to constrain this area, and then you can see that the network updated the feature extraction, the feature, and now this high probability colors are more focused in this to the target layer. And if we add more constraints, like if we have like a layer mask interpret from a well log, then this network will be even more focused to the target layer, right? So here in this example, it shows that there's a prompt, there's like this point box and the well-locking mask prompts actually modifies the way how the model extract the features, and based on this feature, we make the final prediction of the target layer. And now we in this example we want to use this model to interactively interpret all types of geobody layers or geological layers or geobodies in this seismic image. There in this image we have two channel bodies. So for example, if we want to interpret this geobody, we add one point here, and then we see that the segmentation is not good enough, and then we add one more point to get a better result. And to interpret another channel, we can add box plus point constraints to get this interpretation. And then we can also use the same model to interpret the layers, different layers in this image. So now, in this we can get a full interpretation of these geologic features in this in the same seismic image. And another good feature of this framework is that we can easily extend this 2D network for 3D interpretation, because for example, we can start the 2D interpretation with one seismic section, and we can get a first interpretation, the interpretation result in this starting section, and then we can use this interpretation results as automatic prompt for the next nearby interpretation to constrain the nearby interpretation, because this prompt need not to be very accurate, right? For example, for the box, we only need to approximately define the area of the targets, right? And then we can use the previously interpreted results as recursive use the previous interpretation for the next for the prompt as the prompt for the next SNES interpretation. In this way, we are able to get a continuous, consistent 3D interpretation. And here's other examples how it works by using the fine-tuned model to interpret these 3D geobodies like channels, karst bodies, salt bodies, and this fault damage zone. And also there are some other geobodies, which are not included in the training data sets. This model is still able to interpret these geobodies by combine some prompts or some constraints. And in this way, we actually we really achieve the goal by using one model for all kinds of geobodies. So you only need one model to interpret this all these different types of geobodies in all different kind of surveys. For example, as shown in this this video, you can see that this model works pretty well in all different kind of 3D seismic surveys with different types of geobodies. Yeah, and this is the example that I showed previously to interpret these geologic features in one 2D seismic section. Right, so we got all these geologic layers and the two channel bodies. And of course, if we add more constraints, it will be more accurate to interpret these geologic layers. Okay, so now let's move to the second topic, which is about how to build geophysical data sets. And I think this is very important for develop AI applications in geophysics. So in this net, I want to highlight that the shift from previously we called the model-centric AI to the data-centric AI today. And now we are actually moving from focusing on the previously we focus more on like the models, but now we actually focus on more on the data. So in the model-centric approach, we were actually trying to perfect our algorithms or like networks. But today in the data-centric AI, we are realizing that the quality of our input data plays a huge role in the AI applications, which is actually much more than we initially thought. So in fact, we want to see that 80% of an AI's success actually depends on the data, not the algorithm. So instead of constantly tricking models, we are actually now focused on making sure that the data we feed it in is like have quality and reliable. And building on that, the data really is the foundation of an AI system. And here we can see just how critical it is as shown in this slide. So imagine that an AI system is as a compilation of data and algorithms. Well, we spent a lot of time on the algorithms. They actually contribute only about 20% to the performance. And the other 80% that all in the data actually is all in the data. So we treat data like the crude oil of AI. It's what fuels everything else. So this focus on data preparation and ongoing improvement help us actually ensure the AI gets better over time. And actually in geosciences, we face a big challenge. We do not have enough training data sets. And while fields like computer vision have ImageNet and a lot of like standard data sets, benchmark data sets, but geophysics still lacks these similar resources. And this shortage limits our ability to develop powerful AI solutions for geophysical problems. So to address the lack of data in geophysics, we want to talk about three strategies. So the first one is collecting field data using the second one is using simulation models, and the third one is generating data with the AI. And each method adds value in its own way, helping us create diverse and rich data sets for training AI models. So for the first strategy is to try to collect the field data as many as possible, and we are doing this. We have done a lot of efforts to do this data collection, and we already collected and organized nearly 500 field 3D seismic survey data sets, which are all public. We collected all of this data from the internet, and to make the most use of this real-world data, we focus on data curation, ensuring it's diverse and representative. For example, by normalizing and standardizing the key features of the seismic, for example, the amplitude distribution, we create a data set that is not only high quality but also interpretable and diverse. And this process helps us to build a large 2D data sets over which consists of over 200 million sections, which contains a wide range of geological features. And we know that the field data and the corresponding labels often lack diversity, and therefore we do some data augmentation, which is important to increase its diversity, and therefore helps AI learn from a wide range of examples. This step will actually enhance the model's ability to generate across different areas, surveys. And when the field data is not in conclude, for the field data collection, the data set has like high authenticity, but it has no diversity because the amount of data is actually limited, and also it's very label intensive. So then, if when the data set is the field data is not available, then we can turn to geophysical and geological and geophysical forward modeling. For example, we can do all this kind of geological process simulation to build a lot of models with all different kind of geological features like channel bodies, sedimentation. And there's structures, there's 40 and 40 structures, and there's different types of geobodies like karst shown here. And by modeling these geological processes, we can create synthetic data with labeled geological features like channels, like sedimentary fishes, velocity models, faults, horizons, geobody labels, with all different types of geological features. For example, we created by the channel simulation, we created a large 3D data set with all different types of channel labels, and also these are the data sets shown here. We created more than 1,000 3D synthetic set images with all different types of channel bodies, and also we do the structure modeling, numerical structure modeling to create like more than 3,000 pairs of 3D seismic values and the corresponding structure labels like the horizon RGT, relative geologic time values, or the horizon labels, and the fault labels. And also we do the sedimentary process simulation to combine with some geophysical forward modeling. We created more than 2,000 pairs of 3D training data sets with 3D seismic values and the corresponding sedimentary labels. And also we know that this synthetic data is often too ideal and too simple, and which is usually much different from the field seismic data. So then in this, to enhance its realism, we do some domain adaptation, which is very simple. We actually transfer the synthetic data to the Fourier domain to get the phase, the phase and the amplitude spectra. And we also get the corresponding field for the field data set. We also do the Fourier transform. We also get the phase and amplitude spectra. And now we switch the amplitude spectra with the synthetic and the field. And then we combine this field amplitude spectra with the synthetic phase spectra. We will get to the inverse Fourier transform. We get a new seismic data, which will maintain the structure of the synthetic data, but contains the amplitude features of the field data set, so which will look more realistic, but it still has the same structure information as the synthetic, because for the synthetic we'll have the structure labels, right? And this is because we know the phase contains the structure, and the amplitude actually contains the amplitude spectra contains the amplitude appearance, right? So this is the second way of how we do the second strategy, how we help us to construct geophysical data set. And the third one is using generative AI to create a large amount of complex training data sets. So this is the work that we are working on, and we are trying to use the generative AI to do the data simulation to construct structure models. And in this way, we can build a much more complex structure models. For example, here, we use a trained generative diffusion model. We only need to input a fault pattern and a few horizons or layers positions into the model, and then the model this AI model will effectively generate a complex structure models as this one shown here, which actually aligns with the fault patterns and are also very geologically resolvable. And this is a very complex structure model, which will be difficult to simulate by the geological forward modeling, but now by using the AI. Using the generative AI, we can very efficiently to build these complex structure models. And here I want to see that this is very interesting. The very interesting part is that the structure patterns like these ones are actually not included in the samples that are used to train this diffusion model. And the samples that we use to train this diffusion model is relatively is actually very simple, but this trained model is able to generate structurally complex models that is far beyond the complexity of the training samples. And for example, here the training samples do not include structure models of subduction-related thrust faults. However, this trained generative diffusion model can still produce these highly complex thrust structures, like those ones shown here in this net. So therefore, in this way, we can, by combining this AI generation, we can construct more diverse and complex training data sets. So now, in this, by combining these three strategies, we are able to do the data accumulation, to iteratively update the data set to build a more high quality training data sets for developing AI in geophysics. So for example, from the field data sets, we do the data curation. We got a small, maybe like a small data sets, and then to combine the geological and the geophysical modeling to build more diverse data sets, but they are usually very simple. By combining these two, we can build initial data sets to training a generative AI model to generate even more complex training samples. And then by combining these three different strategies, we're able to create a kind of a high quality training data set for training the AI models. And in these strategies, we actually already constructed and published over like 10 geophysical data sets, which are available in this website. And I'm sorry for the Chinese here, but here we show some like samples of this training data set that we created for training our AI models. So to conclude, I want to see that some key points for AI for geophysics. The first one I will say data. So data is the most important, and of course if the data is not sufficient, then another way is another way to enhance the AI performance is to try to incorporate some geological or geophysical constraints into the network as constraints. And also the prompt, the human interaction will be very important to also enhance the performance of AI models. And the foundation model I think is the trend of AI in all different field areas. And here in geophysics, we also try to apply the capability of foundation models. And of course, the computational resources is highly important. And for the academic, I guess we lack this kind of we don't have this sufficient of computational resources for especially for training these large scale foundation models. And for the foundation model, I think I think I will just stop here because it's already like about like 1 hour, right? 50 minutes. So I want to take this opportunity to have some discussions with you guys if you have questions.
Thank you, Xinming, for this very data-rich talk. We have plenty of time, so we can open it up for questions. Either typing in the chat box or feel free to just turn on your microphone and ask the question as well.
Yeah, let me see if I can get some.
We have a question on chat.
Yes. So yeah, this is the question from my friend. He's he's joining BEG, I guess, in a couple of days. So the question is, why do you choose Delta V2? Would your algorithm or framework work for other pre-trained models? Do you test your model on testing data after fine-tuning the model? Yes. So we choose Delta V2 because it shows some like better performance than some other foundation models based on their tests. But this framework also works for any other pre-trained foundation models as well. And did you test your model on testing data after fine-tuning the model? Yes, we show some examples, right, during the slides after the fine-tuning. So the fine-tuning is actually very important if we want to apply this foundation models to geophysics. But I don't know, maybe in the future, these foundation models because the foundation model actually the ability of these foundation models actually improve very fast, like the ChatGPT, right? So now they understand a lot of geological and geophysical knowledge if you ask them this kind of questions. And then maybe in the future, the vision foundation models will also be able to directly applicable to geophysical data. It is possible if they include this kind of training data set, this geophysical data set into the training data set as well. But now, based on our example experiments, the adaptation, the fine-tuning is still very useful.
Thank you. Any other questions?
Xinming, I have a quick question.
Okay.
Yes, sure.
Like, excellent presentation. These are very, very cool work. I never heard about the prompt, and
Okay.
I mean, I know it in ChatGPT, but I didn't know that you can also apply it to to the geophysical data, which are really like very cool. And also the data set you built. I think it would be very, very useful to the community. My question is more on the generative AI. So you use the diffusion model. I wonder if it's only applicable to the processes more like could be like we use the diffusion law to model the process, or it's more applicable to all different kinds of processes.
Yeah, I think so. Yeah. So I think this will be so some of our students is also thinking about that and work on the topic that you just mentioned. Yeah, we are thinking about using this generative AI to speed up the geological, the full simulation of geological and geophysical process, right? Because the numerical simulation is still like computational costly, right?
Right.
So it will be useful if we can use AI to speed up this process or some step of this processes. Yeah, but based on this experiments that we did on this structure modeling, this is actually works better than what we thought previously. You know, because this complicated file patterns is never included in the training data sets. But after the training, this model is able to generate this kind of structure patterns as shown in this model, which is consistent with the faults, right? And also the horizons. Yeah, so this is actually very we are very exciting to see these results. And also, for example, if you look at this example, this subduction zone structures, we never have this kind of structure, these faults in the training samples, but it is still able to generate these patterns by input this sketch of the faults and the geological layers. Yeah, so yeah, it is really powerful. This diffusion model.
Yeah, cool. Thank you.
Yeah, and we actually extend this for 3D as well. So yeah.
Thank you. Any other questions? All right, I see. Oh, yeah, that's a clap. Yes. Looks like no other questions, so we can probably stop here. And Xinming, thank you again for this very interesting talk, and thank you for staying up so late to give this talk. And thank you everyone for attending, and I hope to see you back again next week.
Cool.
Okay.
Bye, Xinming.
Bye-bye.
Yep.
Thank you all. Thank you, Xinming, again.